Welcome back, Leo Lions. This is Mrs. Morgan with today's lesson over exponential growth and decay. So this is Chapter 7, Lesson 7 in your book. So I'm first going to go over the three different types of formulas: exponential growth, compound interest, exponential decay, and then we're actually going to apply them to some actual story problems. So y is always going to be the final amount. So that's what we're going to be solving for. And remember, sometimes you may see that as the f of x, the function of x. But with our equation, this is our y. So y is always the final amount. That's what we're solving for. A stands for the initial amount. So initial meaning the beginning. Where did, whatever the story is about, where did the number start out at? So y equals A. And then in parentheses, so we have to do this part first, 1 plus R stands for the rate of growth. So this is always going to be a percentage, and then we do want to change that percent to a decimal. So it's a percent. That's an easy way to find the R value. And then percent changed to decimal. So for example, let's say our rate of growth was 25%. Well, then we would change 25% to 0.25, and then we would add that to the 1. So it would be a growth of 1.25 inside that parentheses, the 1 plus R. And then T, again, I apologize, hard to see some of this. T represents time. Now, that 1.25 that I was just talking about, so this, what's inside the parentheses, that's what we call the growth factor. Now, it is very similar, so I'm actually going to jump down to the exponential decay because it's very, very similar. There's just one difference. The difference is that our number is going to be going down. So again, this is y equals, y represents our final amount. That's what we want to solve for. The A still represents our initial amount. So where did the number start out at? And then inside here, instead of adding, we're going to do 1 minus R. So the rate, it's still going to be a percentage. And you want to change it. So I'm going to do the same thing. You want to change percent to decimal, and then do 1 minus that rate. So for example, that 25%, I'm going to use that same rate. So it would be 0.25, but instead we would do 1 minus 0.25. So our rate of decay would be 0.75. Okay? T still stands for time. And then instead of a growth factor, this is going to be our decay factor. Okay, now compound interest, again, a similar equation, except that we have to take into consideration how many times is it going to be compounded per year. Okay, and up here, I'm going to write what I did down below and show you the 1 plus 0.25. That's where the 1.25 came from. Okay, so y still equals your total amount. That's what you're solving for. There's a big capital P, so P represents the principal. So in this case, the principal is just like your initial amount, so the starting amount. Okay, that is also always your amount of money. R does stand for your annual interest rate. So this is a 1 that always stays. So 1 plus and then is R divided by N. So R represents the annual interest rate. T doesn't change, stands for time, but N represents the number of times that the interest is compounded per year. So number of times the interest is compounded per year. So sometimes you will see it as annually. Annually means once a year. So that would just be a 1. So it would just stay the rate. Sometimes you may see it as semi-annually, so twice. You may see it as quarterly, so 4 times a year. So we always want to divide by the number of times that it is compounded. Now, this is all set to an exponent of n times t. So the number of times it's compounded per year times the number of years. Okay, so those are our 3 formulas. Now, if you go back in this same folder, and sometimes Shobi just does this to me, so I'm going to have to go back in. But if you go into that same folder, there are 2 documents in there. So we have all of our equations, our formulas there, and here we have some story problems. I'm going to do a couple with you and then let you do the rest on your own. So this is set up pretty nice where we first identify what is the A, the R, the T, and then we plug it into that formula. So I'm going to start with exponential growth. The sale of McDonald's for 1 year is $650,000. Their sales are increasing, so we know that amount they're making has to go up, and it's at a rate of 4% per year. So what will their sales be after 5 years? So I've gone through and picked out those important details. A, remember, is the initial value. So right now their sales are $650,000. That's our initial value. The R is always your percent, so that is your 4%, but I'm going to write it down also as a decimal right away as 0.04. Remember, move your decimal 2 places to the left. And then T, we want to know after 5 years. So once we have those details, then we can just set up our formula, plug everything in the right spots. So Y equals A. A is 250,000. Then in parentheses, we have 1 plus the rate, 0.04, and this is all raised to the 5th power to the number of years. Okay, we can take this a step further. In the parentheses, make sure we follow order of operations. So in the parentheses, we do 1 plus 0.04, so it'd be 1.04. That is your growth factor. Now, from here, what I would do is plug this entire thing into your Desmos. If you do 1.04 raised to the 5th power, you're going to get this big long number. If you round that, then that could potentially change it in the end. So what I'm going to do is type in my 250,000 times 1.04 raised to the 5th power, and I did something wrong. It is not 250,000, is it? I think I wrote that down wrong. Wow, and probably some of you already realized that. I'm glad I didn't give you that wrong answer. I apologize. It was, the initial amount was 650,000, not 250,000. So we need to go back here and change that to 650,000. There we go. So McDonald's in 5 years will make $790,824, and we'll round to the nearest cent, so 39 cents. Okay, I'm going to give my answer with a dollar sign since we're talking about sales. $790,824.39. All right, it is bigger than our 650,000, so I at least know I did my exponential growth. Okay, let's do another one. We've got a population of a school is 800 students. It's increasing, so exponential growth at 2% per year. So where will the population be after 6 years? So again, all of our values. Our initial amount is 800 people. The rate is 2%. I'm going to change it right away, 2.02. And then the time in this one, we are going to figure it out after 6 years. So again, let's plug in our values. So this time the initial value is 800. And then we'll do 1 plus our percent, 0.02. And all of that raised to the 6th power. So this will be 1.02. And then again, we could plug this into our calculator from here. So 800, times 1.02 raised to the 6th power, we get 900.9 people or students. Now, what I'm going to do, because this is representing students, it doesn't tell us where to round, so I would give you that answer. But I'm going to round it since we're talking about students. It'd be silly to have 0.9 of a person. So I'm going to say 901 students. And I showed approximately with that wavy equal sign to show I did round that. Okay? So I'm going to let you try the rest of those exponential growth problems. Now on the back side, we do have some exponential decay that I want to show you. So in these, we know that the numbers should go down. They're going to get smaller. So population, we have 2,500. It's decreasing at 3% per year. And what will their population be after 5 years? So initial value, our starting population is 2,500. Our rate, our percent in this case, is 3%. I'm going to change it right away to 0.03. And then our time is 5 years. So again, plug everything into your formula. 2,500. In parentheses, this time we are subtracting since it's decay. So 1 minus 0.03, all raised to the 5th power after 5 years. So 2,500, I'm going to subtract in here to get 0.97 raised to the 5th power. And again, I'm going to plug it straight into my calculator. 0.97. If that value is between 0 and 1, then we know that it is a decay problem, and we know that this value has to go down. So 2,146.8. So again, I'm going to round since we're talking about population. We're talking about people. So 2,146.8. But I'm going to round up and approximate it to 2,147 people since we're talking about a population. All right. And we can check it went down from our 2,500 people that it started with. And one more. The value of a company's equipment is $25,000. And it decreases at a rate of 15% per year. So what's the value of the equipment in 8 years? So the initial value of this equipment is $25,000. The rate, we've got a higher rate of decay this time, 0.15 or 15%. And we're going to figure that out after 8 years. So y equals 250,000. In parentheses, we're going to do 1 minus 0.15, all raised to the 8th power. So 250,000 times 0.85 if we subtract those. And I'm going to go back to Desmos. So, now I want to make sure it looks right, but I think I wrote it down wrong on my answer key. So our $250,000 worth of equipment, we've got 68,000. Oops. So after 8 years, this equipment that was worth $250,000 is now $68,122.63. I rounded to the nearest cent. So 2 place values. Okay? Again, I'm going to let you then